morning all together. Welcome to our today's Let's Talk Science session. Today it's all about virtual commissioning. Commissioning of production systems is often time-consuming. It takes place at the last development step after the implementation of all components of a mechatronic system, a complex final step. In this webinar, we will learn more about the possibility and the method of virtual commissioning using digital twins. Dr. Christa Clifford-Schenke will present us and discuss this topic with us today. He is head of the team of model-based development of self-optimizing production systems at the Fraunhofer Institute of Machine Tools and Forming Technology, IWU, at the Technical University of Dresden. The perspective of Dr. Schenke is saving time is saving money. Virtual commissioning with digital twin can save 70% of the time needed to commission a production system. So we are interested to learn more about it, and the floor is yours, Dr. Schenke.
All right. So thank you for the introduction, Dr. Stefan. Yes, as we heard, today I'd like to talk to you about the method of virtual commissioning and how we can use digital twin to speed up our development and provisioning process for machines and automation systems. So we start with a definition. The objective of virtual commissioning is to detect and correct errors resulting from the engineering of the automation system. That means we use the digital twin to correct our controller code so that we can use the controller code directly for the control of the machine. The first question is, why should we do this? So we have a look on the procedure of the machine provisioning process. We have different phases in the conventional development and provisioning process. We start with the planning phase, and in this phase, the machine functions are defined. We create a concept of our later system based on the boundary conditions and requirements of the process we want to realize. After this planning phase, we have the development phase where we elaborate the construction, the design and dimensioning of our system. And the special in this development phase is that the disciplines that are involved in the development follows one on the other. So the electronic design has to deal with the definitions in the mechanical construction and the software design with the definition in both of these phases before. So if we, for example, realized in the software design that we need another sensor to implement a needed machine function, it would be already difficult to change the determinations we did in the mechanics and electronics and change the whole machine concept. So often changes in this phase need many changes in the phases before. After the development, we have a realization phase where the hardware is built up and the controller is connected to the hardware. And then in the commissioning phase, we test our soft and hardware systems if they function well. If we now have a look at the project duration, we see here a bar representing it, and 15 to 25% of this time are the commissioning time of our system. 90% of these commissioning times are only for commissioning of the control technology of our machine or automation system. And 70% of this are only for fixing bugs in the controller software. So this is a big time amount where we can optimize our commissioning time if we can change our process. When we now look at provisioning process using the digital twin and the method of virtual commissioning, we also have the planning phase with the following development phase. And what we can see here is that development phase could be shortened a little bit. And that's because of the use of the digital twin. So we build up a model in the early stage of our machine design, and this allows us to take into account the different requirements of the involved disciplines in parallel so that the engineers work together. And with the better coordination of the work in these disciplines, we can get better tuned systems and more or better machine functions in a shorter time. After that, we already have the realization phase where the hardware is built up. And what's new now is that we can do the virtual commissioning with our digital twin and with our real control system in parallel to the realization, so that we can save a big amount of time before we go to the real commissioning of the hardware and set up our system to work. What we see is we can have a big time saving. We have 70% of bug fixing in the software. We have a time amount of the development phase we can save. So we can speed up our provisioning process. So what are the main benefits of using virtual commissioning? We have the digital twin that allows us for a parallel development in the different disciplines. We have a better coordination between the developers, which leads to more sophisticated machine functions. And at least we have a higher software quality after the virtual commissioning process that results in a faster provisioning process. So now we know why we should do the virtual commissioning. The next question is how we can do it. At first, we need to develop a digital twin of our system in the necessary level of detail. When we did this, we can set up our control, we can program our controller code, and then we can connect these control with our digital twin to test the software and to correct failures within it. What we also can do besides of that are endurance tests. We can test if there are some collisions between the mechanical components or between the machine and the manufactured part. We can do automated test procedures, and we can test our machine or solution beyond the actual functionality, for example, to test our safety functions or other functions like this. When our machine hardware is realized, we can change the connection to the real machine, and then we can test our hardware system, we can test the electronic functions, and at least the functionality of our whole machine system. When we do this, there are different methods how we can connect our control functions to the digital twin. They depend on the time where we are in the development process, and we see here on a long time we can use the digital twin to prove our controller functions, and at last we have the real machine hardware where we can test the control system. The readiness level of the controller program rises along this process. So at first variant, we have the model in the loop simulation. This is used in an early stage of our machine development, and here we have our controller function as logical model, which we can integrate directly in the digital twin, so that we have the demand values by this logic in the digital twin. In the later phase, when our simulation, when our control system is defined and we know the manufacturer of it, many manufacturers provide a simulation of their controls, and we can connect this simulated machine control to our digital twin via communication protocols as TCP/IP or OPC UA to give the demand values to the simulation model. When we have the real machine control in hardware, we can connect this via the file bus or field bus, for example, EtherCAT or Profibus, to our digital twin, and now we can set up our system in real time. And in the last stage, we have the real machine. We have the real machine control that interacts over the field bus with the real machine hardware. And besides that, we can use the digital twin for cases of predictive maintenance, for example, or the visualization of deeper machine information. So in this short video, I have these examples for you that you can have a look on it, how it works. So at first we have the model in the loop approach, and there are two different variants. We have on the one hand the control panel. Here we have sliders for each axis of the robot. You can see in the right upper corner, and you see in the corner on the left side down the demand value. On the right side you see the actual value of the single axis, and when we move the slider, the robot moves exactly as it should. Another variant is the usage of a lookup table, where the different positions are stored in that the robot should go to. And here we see the sliders are no longer in function. And when we now start this lookup table, we can see that the robot moves again. Now he moves in Cartesian coordinates, so we give the position of the GCP to the robot, and via a kinematic transformation, the orientations of the single axis are calculated and the robot moves as it should. The last variant I show you is the hardware in the loop or software in the loop system, and here we can see the human-machine interface of our real control system. On the left side we see the MC code we want to realize. In the middle we see buttons for start and stopping of our process, and when we now go on with video, we see the program started, it begins to work, and the robot interacts with the real machine function and moves as it should, as it is demanded. So now we know why we should do a virtual commissioning. We know how it could be realized. The question is, for what can we use this method? When we have a look on the machine lifecycle, we see two new phases. After the development process, we see the protection phase and a later possible reconfiguration phase if we want to reuse our system or machine. And here are some use cases where we can use the virtual commissioning. In an early phase, we can do a feasibility analysis, so we can prove concepts for machines and automation solutions with a digital twin and can have a look if it works in our application case. A second example is the virtual safety analysis in a later phase. When we have our safety control and safety systems realized, we can check if they work well and if they do what they need in cases of emergency. We have possibility to train employees, so workers can use the real human-machine interface, the real operation panels of the machines, and can learn how to set up the machines with it, how to set up processes beside the machine is realized or is used for the realization of other processes. Another theme is the simulation of the energy consumption. Here we use models or digital twins of our systems with deeper functionality, so we can calculate the energy consumption for the realization of a process or a single part. And the last use case is the optimization of machine and production system structures. Here we can set up processes, can check if the processes are right, if the interaction between, for example, machines and transport systems work well. So for one of these examples, I want to go in detail now. I have chosen the feasibility analysis in an early stage of our development process. And here we see the feasibility analysis of automation of a welding process. So we had a customer that had a part that for which he liked to have an automation solution, and the question was if this process is automatable, and if it is, how he could do this. So the objective was to determine several parameters for the feasibility of a concept for a robot welding cell. And what was our solution approach here? In the planning phase, we first did a requirements analysis, then we built up a functional model for the functions we need to realize the process. We built up a CAD solution at first, and then we set up our digital twin with the generation of the visual commissioning model. We did a virtual teaching of this model of the control, and then we had a process simulation with the goal of more detailed informations for a later investment decision. And when it's positive, we can also use our digital twin for the development phase that it's in the ongoing design process of our machine. For this analysis, we used the software ISG Virtuos. You can see the interface here, and what we have on the right side is the library of our machine components. So we can put these machine components into the model, connect them with each other, and when we go on, we see how our solution grows, and we have all the needed components within our simulation model. Here we see the teaching. As I described before, we have these sliders to give the orientations of the single axis to the model, and there we can bring it in the position. For the different points, we need to realize our welding seams, and so we create the program. The robot will follow later. The other sliders are also to move it in Cartesian coordinates, which we not needed in this case. So now our teaching is done, and we can start our process simulation, and we can see here the robot follows the welding seams, and now we can try different robots in this concept, can test them if they fit. And in the last example, we can see we have chosen a very big robot. We have a collision with our manufacturing part, and this robot won't fit our requirements for this process. So what are the main facts of the feasibility analysis? We can create and test automation concepts at low cost in a virtual environment. We have a fast and descriptive visualization as basis for an interdisciplinary development process. We can generate statements on automation options and achievable cycle times as basis of investment decisions. And we have the time saving in the later process for real commissioning by using the digital twin for the virtual commissioning. So typical project times for such analysis are around about 2.5 months, and the costs are 5 to 10% of the later investment volume for the automation solution. So if you are now interested in the method of virtual commissioning, I have a few opportunities how we could cooperate in this theme. So if you are not sure if you should automate your processes, we can do a feasibility analysis together. We have a workshop with our expert to get the knowledge of your application case, and then we provide you an offer for the development of an automation solution and the preparation of the specification sheet. If you'd like to learn more about the virtual commissioning, we have the possibility to offer you a training on the virtual commissioning methods. So after this training, in this training, you learn how to set up a digital twin, at first on a use case, on a training use case, and later on your own application case. You learn how to connect the digital twin with your control system, and you learn how to perform the virtual commissioning on your own. And if you're familiar with the virtual commissioning and you like to participate in its future development, we are in the implementation of the industrial working group. Here we solve specific stakeholder issues in collaboratively funded projects, so we can be part of a network which provides solutions, which provides new model elements, new model functions for the virtual commissioning method. Yeah, if you now have some questions or you like to use one of our offers, please contact me. If you need more information of what we're doing and what we're doing besides the virtual commissioning, please visit our blog, kognitiveproduktion.de. There you can find a variant of different contributions on our themes. And yeah, at this point, thank you for your attention.
Well, thank you, Dr. Schenke. This has been very interesting. I have just in the beginning one major question. At the end, you already mentioned the topic of training and specification sheets. So, because a lot of companies in the field of machine tools, not necessarily robotics, but machine tools who are automating their systems are small and medium-sized enterprises. So what is their necessary setup to step into this functionality? Do they have to have specific software? Can they use their existing software in design and development? Are there open standards for interfaces, getting the data into the digital twin, for example? I think so. These are aspects for them to step into it and to use it.
Mm. Yeah, so you cannot use the conventional software we use in the development process. So we need a special software for virtual commissioning, which is able to contact with the control systems. That's the one. The interaction between models is possible over the CAD construction models, so we can use them for building up the digital twins in the virtual commissioning software. There are several different systems in the market, so yeah, it's at the customer to choose one of this.
Okay, so you can run the geometrical data out of the 3D CAD, but as you have shown, you want to, for various aspects, you want to control movement, function of the robot in this situation. There might also be various controllers involved. So is it focused on one controller, or is it open to integrate various controllers that are used depending on the customer you have?
It's open to use several controller systems, so we can connect different systems to the digital twin, depending a little bit on the software for the visual commissioning we use. It's not every software is suitable for every control system manufacturer, but it's possible, and it's sense of it to use the real machine control we want to use later in our application. So yeah, that's the central need of the virtual commissioning, that we can use the different manufacturer controls.
Okay, I think for this reason it is of great importance, as you mentioned at the end, to give service and support if companies want to step in by specifically also training using digital twins. So I think it's an interesting step forward. We have all learned in the pandemic that such digital functions are not only useful in the situation of saving money, but also not being able to do something in real. I think there are various perspectives for such virtual functionalities. So thank you for your interesting input, and as I see, there are no further questions. So thanks to everybody listening, and be back end of next month for our next Let's Talk Science. and goodbye and have a nice day.
Thank you too. Goodbye.